Hello everyone. So, this is lecture 5 of the 6th week. Yeah, in the previous lecture we looked at a proof extensively, the proof that when you minimize a quadratic function using DFP method, we achieve the solution in n steps, and we also converting the H matrix in n steps. So, there is one more proof that is pending for DFP method. We will quickly finish this and then move to BFGS method in this lecture. Okay. So, yeah, the theorem is as follows. So, consider minimizing f using DFP method where the step size or rather alpha k is chosen using exact line search. Then Bk positive definite implies Bk plus 1 is positive definite. Okay. So, that is a good property, just that there is a caveat saying that you must choose alpha k using exact line search for this for the proof of this theorem to hold. Okay. So, yeah, let us go ahead and prove this. Okay. So, note that, so yeah, assume Bk is positive definite, okay. Then we need to show that x transpose Bk plus 1 x is greater than 0 for all x not equal to 0. Okay. So, yeah, let us see what is x transpose Bk plus 1 x. So, that is, so yeah, I mean we know what is Bk, right, we have this expression here. So, let us just use that x transpose Bk x plus, so we will have x transpose delta k transpose x by delta k transpose gamma minus x transpose Bk gamma k transpose Bk x by gamma k transpose Bk gamma k, right. So, I will write this as follows. X transpose Bk plus 1 x is, yeah, so x transpose Bk x is fine. So, this I will write it as yeah, x transpose Bk gamma k the whole squared by gamma k transpose Bk gamma k. Okay. So, again that is nothing fancy, I am sorry, yeah. So, I have written the numerator as x transpose Bk the whole squared, because I mean these are scalars, and I mean they are just the transpose of scalars. So, I mean I can very well write them as squares, and similarly I can write this as x transpose delta k the whole squared or delta k transpose x the whole squared. Okay. So, define A as Bk power half x and B as Bk power half gamma k. Okay. So, note that Bk is a positive definite matrix. So, that means I mean you can find a positive definite square root of Bk, and that comes by diagonalization. So, I mean that is in case you have learnt diagonalization in linear algebra, you would have known this. Okay. So, I am just taking that particular matrix. Okay. So, note that in this case we can write x transpose bk plus 1 x as yeah. So, yeah, when you take the LCM, it is x transpose bk x into gamma k transpose bk gamma k, which is A transpose A into B transpose B, okay, minus this is actually A transpose B the whole square by B transpose B. Yeah. So, I have just multiplied and divided by B transpose B, which is this. Okay. So, the first term becomes A transpose A into B transpose B by B transpose B, minus this is A transpose B the whole squared by B transpose B. Okay. And yeah, this let it remain as such. So, yeah, the first the numerator of the first term is just I mean is non negative, follows from Cauchy-Schwarz inequality, right. So, you know this, right. Modulus of the dot product of A comma B is less than or equal to norm A into norm B, which is the same as writing yeah. So, when you square it on both sides, it is A transpose B the whole square less than or equal to A transpose A the whole square into B, sorry, A transpose A into B transpose B, right. So, thus you can see that yeah. So, this is Cauchy-Schwarz inequality. So, therefore, you have yeah, A transpose A into B transpose B minus A transpose B the whole squared is greater than or equal to 0. So, it can be 0 also, but I mean that happens only when A and B are in the same direction, that is A equal to lambda B, where lambda yeah where lambda is non-zero. Okay. So, yeah. So, yeah, lambda can be 0 also, I mean then it is trivially true. So, you can say A equal to lambda B. Okay. So, fine, yeah, that is very clear. Now, delta k transpose x squared is also positive, but delta k transpose gamma k we do not know yet, right. So, yeah, so this is proving the positivity of this requires yeah, this in the connection that I just mentioned, where I say that yeah, alpha k is chosen using exact line search, right. So, you need that to prove that delta k transpose gamma k is positive. Okay. So, delta k transpose gamma k is delta k transpose into g k plus 1 minus g k, right, but delta k transpose g k plus 1 equal to 0 when we use exact line search. You can ask how? We showed this here, right. Yeah. So, when we use exact line search, g I plus 1 transpose delta I is equal to 0. So, that is exactly what I have written here, g k plus 1 transpose delta k is equal to 0, right. So, this and this are exactly the same. Okay. Yeah. So, we saw that delta k transpose g k plus 1 is equal to 0 when we use exact line search. So, yeah, now delta k transpose gamma k is just minus delta k transpose g k, okay. But note that delta k is actually alpha k d k. So, we have minus alpha k d k transpose g k, but d k is minus g k b k, sorry, minus b k g k. So, you will have alpha k g k transpose b k g k, and this is greater than 0 for all I mean g k non-zero when b k is positive definite. Yeah, so you have alpha k g k transpose b k g k is so I claim that it is positive for all g k non-zero. So, that is because b k is positive definite, right. So, what have we shown? We have shown that so yeah, this proves that x transpose b k plus 1 x is greater than or equal to 0 for all x, okay, yeah, not equal to 0, for 0 also it is 0, not a problem. But that means that only means that bk plus 1 is positive semi definite, right. So, to prove positive definiteness you have to show that for all x non-zero x transpose bk plus 1 x should be greater than 0, right. So, let us see if that is true as well. Okay. So, x transpose bk plus 1 x will be equal to 0 only when yeah, the numerator of both the terms are equal to 0, right. So, that means we know that the numerator of the first term is equal to 0 by Cauchy-Schwarz inequality when, so yeah, A transpose A into B transpose B is equal to A transpose B the whole squared if and only if A is equal to lambda B for some constant lambda, okay, or some scalar lambda, right. So, note that A is bk square root of bk into x and B is square root of bk into gamma k, right. So, since bk square root of bk is positive definite matrix, that is a non singular matrix, right. So, these are going to be unique. So, therefore, yeah, so this implies that x will be equal to lambda into gamma k. Okay. So, that is the this is the condition when A transpose A B transpose B minus A transpose B the whole squared is equal to 0. Okay. So, yeah, the first term A transpose B trans A into B transpose B minus A transpose B the whole squared, that becomes 0 when x is equal to gamma k, right. So, let us check if at x equal to lambda gamma k does this term become 0, right. So, yeah, delta k transpose x equals lambda delta k transpose gamma k, but we just saw that delta k transpose is actually greater than 0, right. So, this is greater than 0, yeah, at least when lambda is non-zero, right. So, yeah, if lambda is 0 then x is 0, right. So, yeah, but we are only considering for cases when x is x not equal to 0, right. So, yeah, I can say lambda not equal to 0 when x is not equal to 0, and yeah, so when you can see that delta k transpose at this x is positive. Okay. So, it never happens that both of them are 0 together, A transpose A B transpose B minus A transpose B the whole square and delta k transpose x, they never become 0 together. So, that shows that x transpose bk plus 1 x is greater than 0 for all x not equal to 0, and which implies bk plus 1 is positive definite. Okay. So, note that bk plus 1 I mean may turn out to be something other than a positive definite matrix only if delta k transpose gamma k is not greater than 0, right. So, yeah, for example, if it is less than 0 then yes, we could have bk plus 1 to be a matrix that is not positive definite. Okay. So, this is a proof. Note that, but we are minimizing f which is a general f, it need not be a quadratic function. So, in case we can try and construct an exact line search for the f using exact line search, then it is good to use that for DFP method, because yeah. So, while minimizing a general function using DFP method, okay, so we can I mean in case it is possible to use exact line search, we I mean it is good to do so, because we would not get problems like what we got for x1 squared e power x2 plus x2 squared e power x1 when we are starting with minus root 2 minus root 2, right. So, there we actually got bk plus 1 to be a matrix that is not positive definite, because of which dk equal to minus bk gk was not a descent direction. Okay. So, alright, yeah. So, this is all I had to say about the DFP method. Now, we will start with the BFGS method. Okay, so this is named after Broyden, Fletcher, Goldfarb and Shano. Okay. So, yeah, here again the difference between the rank 1 correction DFV method and BFGS method is just in the update step BK plus 1. Okay. So, yeah, I will just write it down, just BK plus 1 equal to BK plus 1 plus gamma k transpose BK gamma k by delta k transpose gamma k into delta k transpose by delta k transpose gamma k. So, note that this is a scalar and this is delta k transpose is a matrix, okay, minus yeah. So, this is delta k gamma k transpose Bk plus Bk gamma k delta k transpose by delta k transpose gamma k. Okay. So, yeah, I am not deriving this since I think I mean we have spent quite a bit of time in DFP method. Okay. So, but nevertheless, yeah, this is I mean both of these methods are actually called as the Broyden family methods. Okay. So, I mean we you can also use the convex combination of the updates of the DFP method and the BFGS method as well. Okay. So, I mean even that works. Okay. So, yeah, the algorithm is very simple, it is exactly as what we had here. Okay. So, just that yeah, in this step we need to substitute yeah, this update whatever we have written here. Okay. So, let us actually work out the same problems that we had worked for rank 1 correction and DFP method using BFGS method as well. Okay. So, yeah, let us start with quadratic function with 5 cross 5. Okay. So, yeah, this was this line was for rank 1 correction and this for DFP method. Now, I will write that for BFGS method, it is B plus 1 plus gamma into B at gamma by del dot gamma into, yeah. So, here is a matrix. So, I have to use this none business. So, that is dl none at dl none by again dl dot gm, and the next one is the numerator is the sum of two matrices, that is delta at b at gm of none plus b at gm none at dl by dl dot gm. Okay. Yeah. So, everything else is the same. So, let us just run the code. Okay. So, there is a difference of size is what they claim. Yeah, this is delta delta transpose, that is fine, and this is delta yes, this is gamma transpose B, and so we will write the update step for BFGS. So, that is B plus 1 gamma transpose B gamma by delta transpose gamma into delta delta transpose by delta transpose gamma, and here we have delta transpose. So, this is so delta gamma transpose B plus B gamma into delta transpose, right, by delta transpose gamma. So, let us check if we get the answer. Okay. So, yeah, we got the answer in 5 steps, n steps so as to say, and you can see that it is the same as yeah H inverse B, and you can also see that H inverse and B are exactly the same, right. So, alright. So, yeah, that is for the quadratic functions, and for general functions again we can use this step. Okay. Comment this out and note that I have started with minus root 2 to see if BFGS gives us a respite. No, yeah, we see that it is ending up at the same problem. Okay. But yeah, if suppose I start with let us say minus 0.5 minus 0.5. So, you can see that the convergence happens in 25 steps, or yeah, even if you are in a better position where let us say you are in 1 comma 1 for example. So, there as well you can see that converges in 31 steps. Okay. So, there is actually no difference in the performances between the rank 1 correction DFP and the BFGS method. Okay. So, one more method that not exactly one more method, the one more way of updating BK plus 1 is to use the convex combination of DFP and BFGS, right. So, that is called as the Broyden family. Okay. So, when you say Broyden family algorithm, right. So, it is BK plus 1 equal to phi into BK plus 1 DFP plus 1 minus phi into BK plus 1 BFGS for some phi in closed 0 comma 1. Okay. So, suppose if phi equal to 0, you can see that this is actually the BFGS method. If phi equal to 1, then it is the DFP method, and phi equal to 0 is BFGS, and phi in open 0 1 is a convex combination of both of these method, and I will just implement that as well. You can see that again there will be absolutely no change. Okay. So, let me write this as DFP and this as BFGS, and B equals DFP by 2 plus BFGS by 2. So, I have just taken phi equal to half here. Okay. So, then it is half DFP plus half BFGS, right. So, that is exactly what I am doing here. So, yeah, no change, you have the answer in 5 steps, and your H inverse and the final B matrix are one and the same, right. I can choose some other phi as well, say 0.2 and 0.8 for example. Again it is the same result, you have minus 0.5 and whatever, I mean the answers are the same, and you can see that B n is actually H inverse, right. So, we will do the same thing here as well. So, this is DFP and this is BFGS, and B is DFP by 2 plus BFGS by 2. So, yeah, I have chosen 1 comma 1 as the initial point. Yeah, the answer comes in 31 steps, no problems. And suppose you put say 0.2, or rather if you want me to do this for minus 1 minus 1, yeah, minus 1 gives us the same problem, and maybe I will do it with minus 1.5 and minus 1.5. Yeah, so you can see that yeah, you have an error. I mean it goes to the saddle point minus 2 comma minus 2 when you put DFP by 2 plus BFGS by 2, and for example if you put 0.2 and 0.8, there as well yeah, so for minus 1.5 minus 1.5 the result is the same, you are converging at the saddle point, but if you start let us say at 1 comma 1, yeah, so in 31 steps you converge to the correct solution 0 comma 0. Okay. So, these are all the methods that I wanted to discuss, and the last point about quasi Newton methods is that the performance of all these methods that we have discussed, right. So, which are the rank 1 correction, DFP method, BFGS method, or the broader Broyden family methods, right. The performance is exactly the same for quadratic functions, because yeah, each of them converge exactly in n steps, and yeah, the nth step the matrix B becomes H inverse. So, inversion happens without actually inverting. So, that is how we started with quasi Newton methods, and all of these methods does exactly the same, they perform the same. And yeah, so for the other examples as well, so for most of the examples that we saw, right, where we considered the x1 square d power x2 plus x2 square d power x1, for yeah, certain initial points it converges to the saddle point, and for certain other initial points it converges to the actual solution 0 comma 0, but I mean all the methods perform the same, right. So, not much of a difference. Specifically for DFP method, BFGS method, and the Broyden the broader Broyden family, we I have never in my experience observed any difference. Okay, it's I mean the answers are exactly the same. For rank 1 corrections, yes, I mean sometimes when yeah, the denominator may turn out to be close to 0, if you recall it as delta k minus bk gamma k the whole transpose gamma k, right. So, that might become close to 0, in that case rank 1 correction sometimes had created problems. Okay. Yeah, and that is actually why we actually went to rank 2 correction, from where we actually got DFP, BFGS and the other solutions. Okay. So, I mean this actually completes our discussion or actually the discussion of optimization algorithms for unconstrained optimization. Okay. So, a quick recap of what all we discussed for unconstrained optimization, the algorithms, right. So, we started with gradient descent, where dk was just minus gk. Okay. Then we went to conjugate gradient Fletcher-Reeves, okay, where yeah, d0 was minus g0 and dk was minus gk plus gk plus 1 transpose gk plus 1 by gk transpose gk into dk minus 1. Okay. So, that was the update. This is Fletcher-Reeves, and yeah, then we went to Newton's method, where you had dk equal to minus hk inverse gk, and yeah, in general you had alpha k equal to 1, but for yeah, for damped Newton's method we had alpha k is chosen by the backtracking line search, and for modified Newton you had maybe modified Newton, I will just write it. Yeah, for okay, for damped Newtons it was, yeah, dk was the same, but alpha k by backtracking line search, and the next one was modified Newton, where dk was minus hk plus lambda k inverse gk, lambda k was the minimum of, I mean half minus the minimum of minimum eigenvalue of hk, okay, but alpha k was 1, okay. And then we had the quasi Newton, right. Yeah, in all quasi Newton methods we had dk equal to minus bk gk, but bk plus 1 was updated according to either rank 1 correction DFP method, BFGS, or the Broyden family, the broader Broyden family methods. Okay. So, yeah, this completes the discussion on unconstrained optimization. In the next week onwards we will start with constrained optimization, but the basics of unconstrained optimization will be very necessary. Okay. So, we will build up the discussion of constrained optimization only using the basics of unconstrained optimization algorithms. Okay. So, yeah, prepare this well, so that yeah you get to understand something when you come to the algorithms for constrained optimization. Thank you.